have to stay late anyway.
Yeah, I have a midterm right after that.
You wanted to go home, right? Or something? Somebody told me. Oh, never mind.
With the final.
Yeah, about the final. Okay, that looks good. Come on. So you might have noticed I posted the new project for next week, which is gonna be about differential equations. It sounds scarier than it is. It's actually fairly intuitive thing. It'll be like simulation of like the stretchy rope thing. This time done with dynamics. It's sort of fun. It's also like sort of precursor or like appetizer of physics-based animation, if you will, and ties really closely to eigenvalues and eigenvectors. Let me do a real brief recap. I sort of made this little diagram for myself where we are currently. Oops. So matrices, if I have a matrix, so it can either be rectangular or square. Right? I mean rectangular, not square. If it's square, then it can be defective or deficient. Defective is sort of like bad word, right? But, or non-diagonalizable, and this one will be diagonalizable. Diagonalizable. And diagonalizable, it's either in real or complex numbers. Sometimes we have to go to complex numbers. So these cases, the rectangular and the defective cases, that's essentially yet to be covered, and that's what the singular value decomposition will essentially be sort of taking care of. But currently we are talking about this case, diagonalizable. We like to be in real, but sometimes we have to go complex, and it's not really making that much of a difference. Okay, and what I ended with the last time, so if we are in this diagonalizable case, square diagonalizable, so if I have a diagonalizable matrix A, so diagonalizable means that it has the full set of eigenvalues, right? So with eigenvalues lambda 1 to lambda n. They can in general be complex. They could also be real, right? Real is sort of a subset of complex numbers. By the way, thinking about this, how did the homework go? Did you manage to compute the eigenvalues, eigenvectors in the last example, or are you gonna do it tonight?
Yeah, I guess.
Huh?
That was pretty straightforward.
Okay, good. Yeah, it was that was not meant to be tricky, especially if it's your first encounter with eigenvalues and eigenvectors, just to get it actually done. So the statements I ended with the last time was that the trace of a matrix A, what was a trace? Remind me? The sum of the diagonal elements, yeah. Interestingly enough, it's also the sum of the eigenvalues. And the determinant of A, that doesn't have as simple definition as the trace, right? We have been through that. It's the sum over all the permutations and so on. But the determinant is nothing but a product of the eigenvalues. So this is sort of cool. Like the determinant is not so simple to compute, but trace is very simple to compute. So if you ever want to check your eigenvalue computations, you might want to check them for homework 6, the last problem, the homework, right? It's nothing easier. Just sum the eigenvalues, sum the diagonal elements of the matrix, and these things must be the same. And why? That's what we discussed the last time. It's fairly straightforward argument. By the way, you can also notice one interesting thing, that these lambdas in general are complex, right? But if I started with a real matrix, then the trace and the determinant must be real numbers, right? So these must be real numbers as well. Do you know why? Can you think of a reason? So they must be real, right? Even though the lambdas, every single individual lambda can be easily a complex number. So is there some sort of contradiction in here, or is it fine? Or you need to invoke one thing we were, I was discussing about the complex eigenvalues.
They always come without complex conjugates.
Exactly, they always come in complex conjugates. So if you sum all of them together, then you are guaranteed you are summing the complex conjugates together, and if you are summing two complex conjugate numbers, you get a real number, right? The complex conjugate flips the imaginary part. If you sum it, you get zero imaginary part, you get a real number. Same thing here. If you multiply two complex conjugates, if you multiply z and z complex conjugate, then you get the norm squared of z. So that's again a real number. So this is fine. Indeed, these things always have to be real, even though the lambdas can be complex. So this check also works even if the eigenvalues are complex. Okay, let me close the door. All right, let's take a look into differential equations. So maybe before I show the math, the first slide for differential equations, I can give you like the intuitive picture. What does it actually mean solving a differential equation? Sort of sounds like scary, and you can approach it purely from the mathematical perspective. The mathematical perspective is that I have like an equation which is looking for a function. So the unknown here is an entire function. In this case would be like y going from real to real, or it could be going from, if the domain is time, it's like going from 0 to infinity to real, because we usually don't want negative time. Doesn't matter, either way or it could be like some restricted interval. Either way it's just a function, and we are looking for a function. And the function has to satisfy an equation for all points in the domain, and it involves some differentiation operation. So in this case, the simplest possible differential equation is saying that the derivative of the function has to be some constant a which is given to you, that's a given constant, times the original function. So you can look at it as simply as like purely as a mathematical puzzle, if you will, just find the function that satisfies this, right? But you can also look at it from a different perspective. I mean, it is really the same thing. It's just how you interpret it. You can look at it if I have a two-dimensional vector field. So for like any point, give me any point on the plane, and I have some function which tells me the direction there, the direction which I should go. So then solving the differential equation is equivalent to saying that I start somewhere. Say I start, that's my y0, that's my initial condition. I always need an initial condition to solve it. And then the differential equation tells me at every point the derivative. So here, let's say I would know that the derivative is like this. So I would move there a little bit. And then again, at this new point, I have another derivative. So I can again move a little bit, and here I will have another derivative, again move a little bit, and so on. So, and if I take infinitesimally small step every time, then I converge to a continuous function, right? Or you could say it like, if I'm taking small steps, then as the step size h is going to 0, then I'm converging to something, hopefully. And that something is a continuous function. So like the intuitive, very super intuitive interpretation could be that this is some sort of like stream, which tells you for every point it tells you like a velocity, like water in river or something like that. And I throw a particle at some initial point, and it just gets carried along. And the trajectory of this being carried along, that's the solution to the differential equation. So this picture you can keep in mind, especially if you are not super well versed in calculus. But the mathematics is really not so bad. You don't need a whole lot of calculus here. Okay. Yeah, so let's look at this. This is probably the simplest possible example of a differential. You might have seen it somewhere, have you? Some math class. Right. This is we'll very shortly go to multivariable, but because we are in linear algebra, so we are doing vector stuff. But let's do this. So this y is just a function of one argument and only maps it to one number. So just a plain vanilla function, and it's very easy to just realize that the solutions are just exponentials. So this coefficient a here also appears here. So the t here is the parameter of the function, right? That's the argument to the function. The a is a given constant. It's also like a real number, but this time it's given. And the purpose of this y0 is that it can be anything, really. It is just an arbitrary constant I can multiply the exponential with, and it's still true. So I could also write it like c. So if I take an arbitrary function c, where c is like a constant. If I take a function like this and I take its derivative, then what I get this. So the only thing you need to know from calculus here is that the derivative of the exponential with the coefficient a is just a e to at. And this is where is it? Yeah, and so this is just a times my function, right? If I said that yt is c e a t. So instead of, so the c is exactly the value of the function at 0, right? Because because e to 0 is 1, so y at 0 is the c, so we can just call it y0 instead of c. Did I make some mistake? I'm looking at it suspiciously. I was essentially just like rewriting. I was just, my whole point was that this is arbitrary. This is the initial condition. This is like when I was showing this example, this is where we drop the particle to begin with. And it can be dropped anywhere, right? If I drop it here, I get some other solution. If I go over here, I end up with different solution, and so on.
Where do you lose c?
Huh? We lose c because I say that c is defined by y0, and y0 is arbitrary. I guess you could twist it this way. You could say that an arbitrary solution of this differential equation is this c e to at, and once I fix initial condition, once I fix the y at 0, then you easily see that y at 0 has to be equal to c. So essentially I didn't have to introduce the c at the first place. That's what like the slide was implying, and just call it y0 to begin with. It's just like a subtle nuance there. What is important to remember, that the multiplication by a constant doesn't make a difference in differentiation, right? Because differentiation is a linear operator. So if a function is a solution to the differential equation, then its scalar multiple is also a solution. That's what the c meant, and it translates to the fact that we can arbitrarily pick an initial condition. Only once we pick the initial condition, we have a unique solution. If we don't have specified initial condition, we have a whole family of solutions. Yep, just like keep this analogy in mind. Like if I have this stream and I have a choice, where do I drop? Like you are at a river, you can like throw a stone or maybe something that flows there. So you can throw it anywhere, it will get carried away, right? But to be able to compute the trajectory, you need to know where you threw it to begin with. Okay? And this is just a definition of exponential. This is just the Taylor series for exponential. Sometimes the exponential is just defined using this. You can prove that it always converges for arbitrary a. By the way, when we talked the last time about the Euler equality e2I theta, where I was the complex unit, I was saying that this is equal to cosine theta plus I times sine theta. You can prove this easily also from the Taylor expansion, because if you plug in here the complex number I times theta, then you just then you realize that I squared is -1, right? And I to 4 will be 1, and so on. And this series splits into two series which exactly correspond to cosine and sine. So this is how you can prove it if you wanted to. I mean, we are not doing calculus here, so I'm not gonna do there. I'm just pointing out this connection with the previous lecture. Okay. So we are in linear algebra. So what we want to do is to do vector differential equations, because the 1D ones are really not that exciting. I guess already for the example I'm using here, when you have like a flowing river or something, already there you would probably want something 2D, right, for x and y. So the good news is that for vector valued functions, it doesn't really change all that much. So if I have so in this case, I'm looking for two functions. I can either look at it as two functions y1 and y2, which are both from R to R, or I could be looking at it as a vector function which goes from R to R2, right? And then you can just say that y is just the components y1 and y2. And those are functions because all this depends on some t. That's what makes it a function. The t you can interpret as time if it's like a flowing river. So this is so if I have a vector valued differential equation like this, so I'm looking for two functions y1 and y2 that satisfy this equality, which can also be written in matrix form using a diagonal matrix like this. And the solution, of course, is the same as the solution for the individual equations, right? Because they are not related in any way, right? Here I'm asking for y1 such that the differential of I1 is lambda 1. Sorry, y1. And I keep saying y1. Y1 is lambda 1 y1, and the same for the second one. So they are totally unrelated, right? You just apply what we just said for 1D functions individually to each component. So the solution, of course, is just the e to lambda 1 dy1 at 0. That's the initial condition for the first component. It's the initial condition for the second component. And you could also write it, if you want it, in a matrix form. That will be actually useful. The following. So here are the initial conditions for both functions, and here is essentially the matrix solution, the matrix exponential, as we will see soon. So this was a really simple example of a vector differential equation. Let's look at a little more realistic example. So here I'm already writing as a function, so this boldface y, which I like when I handwrite it, I put there the arrow instead of the boldface. Now this is a function from R to R2, so it's like this R is like time, and the R2 are the two coordinates, x and y. And now my differential equation looks like this. I want the time derivative of y as a vector now, x and y, they're differentiated in time, to be equal to yt times some matrix A, where A is an arbitrary, but we assume it's diagonalizable matrix. Why we assume it's diagonalizable is because we want to pull some eigenvalue eigenvector tricks. That's the whole point here. So before this example before was the special case where A was a diagonal matrix. Right? If it's a diagonal matrix, lambda 1 and lambda 2, we already know how to solve it. We just do this, right? But when there are relationships between the first and second coordinate, between y1 and y2, am I saying this right now? y1 and y2. Okay, good. So when there are relationships and they are captured in the matrix A, so what does it really mean? It means that the y1 first derivative will be a11 y1 plus a12 y2, right? If I write it by coordinates. And here, like this. Right? This is what the fact that this is a function doesn't really matter. I just take the values at any given time and multiply it by the matrix, right? That's all the function does. The fact that the function is important when I am taking the time derivative here. Okay, so how do we solve this? Using eigenvalues and eigenvectors. That's why we assume the matrix is diagonalizable here. So here is what we do. So I take the diagonalization. So V will be the invertible matrix of eigenvectors, and lambda will be the diagonal matrix of eigenvalues. That's what we had the last time. For a diagonalizable matrix, I can do this. Not always in the real domain, but sometimes in the complex domain, but it can be done. Now, because V is invertible, I can just put it on the other side. I can multiply the entire equation by V inverse, right? So that this V disappears, and instead V inverse appears here. And what I have here is V inverse Y and V inverse Y. So this is like begging for the V is constant, right? Because A was constant. Oh yeah, remember this. The A here are really just numbers. Those are not functions or anything like that. Those are just constant scalars. Only in this case, it reduces to essentially eigenvalue, eigenvector. It reduces to linear algebra. You can have more general differential equations where that's not the case, but then it's not as simple as this. So how do we solve this? Well, now we have this form. It's begging for a substitution. So we do this substitution. We say that the V inverse Y is Z, and because V inverse is constant, we can do that. Of course, we can revert from the substitution by saying that Vz is Y, right? Again, we multiply from the left with V, and that's it. But this system, if this system we get for, oh, this looks like a bug, right? There should be Z. No. This is correct. Sorry. This is okay. This is what we get when we plug in the Z. So we get that the time differentiation of Z equals lambda Z. But the lambda here is a diagonal matrix, right? It's a matrix lambda 1 to lambda n. Everywhere else are zeros. That's a matrix of eigenvalues. So this we already know how to solve, right? This is what I was showing before. We would even know how to solve it for more than 2 by 2. It's just a diagonal matrix. The point is that the coordinates now are decoupled. If it's a diagonal matrix, then it means that it just multiplies every single coordinate of the Z by some scalar. So the coordinates don't couple together, like in the case of a general matrix. So the solution is just like before. For given initial conditions at 0, where do we drop the stone or both or whatever? And this is just the general solution of the differential equation. Here just we take the exponentials of the eigenvalues, and the lambda 1 and lambda 2 are the eigenvalues there. So this is the Z, and if we want to get, and we probably want to get the original solution Y, we need to revert back from the substitution. But that's easy, right? Because what I had there before was that Z is just V inverse Y, right? So that's what I plug in here. Instead of Z0, I can write V inverse Y0. And instead of Vz, I can just put Y, right? Because Vz is just Y. So the final solution is exactly this. So this is the matrix of eigenvectors. So here are the eigenvalues raised exponential of the eigenvalues with the time. That's the only place where the time enters, where the parameter of the function enters, and here are the eigenvectors inverse. And that's the general solution. There's another way to write this, which is sort of elegant. That's using a matrix exponential. Have you guys heard about matrix exponential before? Good. I have the pleasure to be the first to tell you about matrix exponential. You will hear about it probably many more times. It's also related to Lie groups and Lie algebras, particle to Lie algebras. But I will not make this connection right now. Later you will see that probably. So what we have already done basically is the matrix exponential, but we can look at it in a different way. So we can look at it in this way. If we have a square matrix, we can define the matrix exponential simply by taking the Taylor series and plugging there the matrix. Let me look at the old slide just to give you a comparison. This was the slide. So this, when A is a scalar, then the Taylor series looks like this. That's how exponential can be defined. And this thing for a matrix, I just say, well, why don't I just plug there a matrix, right? I know how to raise matrix to arbitrary power, just do matrix multiplication. I know how to sum matrices. I certainly know how to divide matrices by a scalar, right, by these factorials. So this is perfectly well defined. Well, you could catch me here. Is it really well defined? And I would answer yes, because this power series, or is it power Taylor series, always converges. For any matrix A, it is convergent. Could prove this. We will not be proving it. I guess the intuitive reason is that the factorial grows fast enough that it wins over the matrix and it converges to something. That's not really a proof. So in the particular case, if we have a diagonalizable matrix, so the matrix can be written like this, then the powers become very simple, right? That's what we discussed the last time. Then the powers become just this. That's because, like, if I took second power, that would be V lambda V inverse times V lambda V inverse. But the V inverse is just identity, right? So this is V lambda squared V inverse. And if I go to power k, I just get k here. So the eigenvectors, they don't care. The only thing that happens when I'm taking powers is I could as well be taking powers of the eigenvalues. And therefore, the same thing is also true for the exponential, right? Because exponential of a diagonalizable matrix then is nothing but the eigenvector matrix, and here I take the exponential of the diagonal matrix and the inverse eigenvectors. And the exponential of a diagonal matrix, that's simply just taking exponential of every single diagonal term individually, right? Because again, this just splits into n independent equations. When the matrix is diagonal, it's all decoupled. So this is how we can write a general solution to a vector value differential equation. So general equation doesn't have to be 2 by 2. It doesn't even have to be real. General solution looks like this. You take the exponential of at, where a is now a matrix. You take a vector of initial conditions, whatever the dimension of the problem was, and that's the solution. So as I was saying, it's really not that bad. Like, notice the similarity to the 1D case. The 1D case looked just like this. It was just exponential e to at times the initial condition y0. So the only difference here is that now we have vectors here, and here we have the matrix exponential. So that's like direct generalization from scalars to vectors and matrices. So that's sort of cool that it works here. Is that sort of clear? Okay. Right. So let's look at spring mesh Dasphot system, aka damped harmonic oscillator. You might have seen this in some physics class, because this is sometimes discussed in physics. And this essentially leads to the project. Your project for the next week. I just posted on Canvas. I hope I posted it correctly. Maybe you can check if you are online. So what's the deal here? So this is just the 1D case. So I assume we are oscillating about some zero state, and the model it's like a very simple physical system. It's a classical example of a dynamic system governed by a second order differential equation, and I'll explain in a second how do we deal with second order differential equation. Why do we need second order is because the nature essentially is second order. That's the Newton's second law, which relates forces and accelerations. And before, actually, I should not ramble so much. I need to cover that. I just wanted to tell you that before people were thinking that nature might be just a first order system, and we might get away with just first derivatives. But I think it was Newton, who realized that we actually need to go to second order derivatives, so we are able to model the nature appropriately. So the physics system here is just like a mass point attached by a spring to the rest configuration. The spring has some spring constant K, so it's like huge K, that means like really stiff spring, like really strong steel. If it's low K, then it's like something mushy, something like rubber or something. And the other thing we have there is the Dasphot, which is just a damping term. You could also think about it as like a resistance of the environment, like that this is not in a vacuum, but it's some sort of environment. So if it's like in air, there will be some air resistance, which will be a force acting against velocity. So maybe it makes more sense from this equation. So this equation, that's the equation of motion for this damped harmonic oscillator. And what is it saying is that, this double dot means twice differentiated with respect to time. So the one dot means one differentiation with respect to time, and second dot means differentiate second derivative with respect to time. So second derivative with respect to time is acceleration. And from Newton's second law of motion, we know that the mass times acceleration is equal force. And the forces acting on the spring, on our mass point here, is the spring force. That's the first one. So that's minus kx. That's just saying that if the spring is stretched, if the point is over here, then the point wants to return back. This is Hooke's law. It wants to return back the further the spring is stretched. So that's why it's proportional to x, and it's proportional to k, which is the spring constant. It just tells us how strong the spring is. The k should be non-negative, otherwise it would be a weird spring. X dot is the velocity, right? X double dot was the acceleration, X dot is the velocity, and this term is the velocity proportional damping. So this is just a term saying that if the point is moving with some velocity, then there is some environment that resists that motion. Like imagine like you are like a submarine or something, or even you are swimming in water, then the water resists your motion, right? If you have some velocity, then there is a force of the environment pushing you against that velocity, essentially slowing you down. Similar like friction. But so that's the second term. That's the damping term. And this is just like a 1D second order differential equation, right? 1D because the x is just a function of time, so from r to r, or from 0 to infinity to r. So you might have seen this in physics, but here we convert it again to linear algebra. So now we want to solve it and study the solutions of the damped harmonic oscillator. So what do we do to convert it to the previous case? It's a standard trick to convert second order differential equation to two first order ones. And the way we do it is this. So this is really just the equation rewritten, but we introduce an auxiliary variable for the velocity, all right? And here it's like sort of dumb equations, like velocity equals velocity. Well, of course it does. But the point of it is that then I take this expanded state vector, this velocity and position, and here on the other, on the right hand side, on the other hand side, will be is the same state vector. So really the bottom equation just really says that the time derivative of x, the x dot is again just the time derivative of x, right? So this one says that the time derivative of x is really the same as this. So the point is that here I introduced an auxiliary variable and I am just tying the two together. I'm saying that the derivative of the second one will be equal to the first one. That's the trick how we convert second order differential equation to two first order ones. And we have to deal with that because we need to work with acceleration so that we are able to simulate dynamics. And the first one is the differential equation we begin with. So now y is just a two-dimensional vector consisting of velocities and positions. If you will be going to physics-based animation, this is also what we will be studying a little bit more. So how do we solve this? Well, we know how to solve this, right? Or what do we need to do to solve this differential equation? So what we need to do is to compute the matrix exponential of this matrix A. Actually, let me just copy it here. So the matrix A is this. It's minus c divided by m, minus k divided by m, 1 and 0. So that's this matrix A. To solve it, we need to do the matrix exponential. That's also what you will need to do in your next project for a little bit more complicated system. We will get there. So, so the only tricky part there is to finding the eigenvalues and eigenvectors of this matrix, right? So let me quickly do it here. So I need to compute the determinant of the characteristic polynomial. So this is the characteristic polynomial, right? Which, if I'm not mistaken, is this plus k divided by m. So all the minuses nicely cancelled, which leads to lambda squared plus c over m lambda plus k divided by m. And that equals 0. So this is my characteristic polynomial. And this is again just a quadratic equation, right? So I apply the well-known formula. I multiply it by m. And then apply the formula. So this is minus b plus minus b squared. That's, oh, this is like if this was a, b, c. B squared minus 4ac divided by 2a. So those are the two roots, and based on what these lambdas are, we can characterize different possible outcomes of the damped harmonic oscillator. It's sort of cool. So the first case is if the damping is low, if damping C is small, right? If we have this, if it's smaller than Km. So what was the M? M was the mass of the mass point. K was the spring constant and C was the damping coefficient. So the first case means that the damping term is weak. In this case, what happens? In this case, we have complex eigenvalues. We know that we should not shy away and just like deal with it, because in this case, it's actually sort of cool. Because like what would you intuitively expect from a system like this? That I have just a 1D system. I have a spring and I have a mass point attached to it, and I pull it and I like let it go, right? It's called oscillator. So you would expect it will be oscillating, right? That's exactly what the complex eigenvalues are essentially for. Because if I have a complex eigenvalue, then I will be taking the exponential of it. What I will get is the cosine and sine term, right? And those are the oscillations there. Now there is still some damping. So in general, this solution will look something like this. It will like do a couple oscillations and it will be damping. It will eventually settle, or in infinite it will settle, but it will get there pretty quickly. So the second case is when the damping is real strong, where the c squared is greater than 4km. In this case, the eigenvalues are real and negative, and what this means is that like the resistance of the environment is really high. That I like took this spring and like put it in honey or like something or clay or something that like really resists strongly the motion. So what will happen there? That will like very slowly go to zero. To the rest pose. Like if I stretch the spring, it will go really slowly because there's a really strong resistance. The interesting, that's like the edge case when it's exactly zero, that's called critical damping. That means that it will get to the rest state as quickly as possible without oscillations. Oh, by the way, what would happen if the C was zero, if I didn't have any damping?
Never stop.
It would never stop. Yeah, it would be just bouncing all the time for eternity. Okay, by the way, the fact that this worked for second order differential equation generalizes to higher order differential equations. So if I have like a fourth order differential equation, no problem. I just essentially introduce new variables for the higher order derivatives, and I just tie them together using a matrix like this, and then all I need to do is solve eigenvalues and eigenvectors of this larger matrix. Okay, and finally, I might even end on time. So this is essentially what is your project for the next week, is to do a dynamic simulation of a stretchy string. So you might remember when we were discussing sparse linear systems or examples of linear systems, we had the stretchy string example. So the model was that it's like like a rope or something, so that every point is constrained to move only in the y-axis. So there's no motion in the x-axis whatsoever. So the position of every point is given by y, and those are like springs. So those are like elastic links. So they don't like to be extended too much. When they're extended too much, they push with some force to return back. These endpoints, they are like fixed. They are like attached to the wall or something. So the displacements here, that would be like y0 and y and plus 1, are just frozen to be 0. Now what we do, we write the second order ordinary differential equations. So for this I need some model of forces. So the model of forces, if I'm on some link yi and my left neighbor is yi minus 1, my right neighbor is yi plus 1, oops, ahead of myself, then the force acting on the link number I from this spring is k times yi minus 1 minus yi, right? So it means if this is below, then the force will be acting this way, right? It wants to go back. So it's not really a real spring. It's really just it's a linearized spring, but it works for this example. And there is the contribution from the other spring, which is k yi plus 1 minus yi. So that's again saying there's like another force from the second spring also doesn't like to be stretched, so also pulls it down, right? If like just one was pulling it down, it will like still be pulled down, right? So this is this part of the equation, and this is the damping part. So again, now we again assume that this is not in vacuum, but this is in some sort of environment that resists velocity. So there is a force acting opposite velocity. It is this yi is the velocity of every point, right? The velocity here, of course, has to be 0 because those guys are put, but these guys will be moving. That's the cool thing. We will be simulating the dynamics of this, and there is a force that opposes that motion. So the second order ODE modeling this system for every point looks like this. Here I just group the terms together. The K and C are some parameters. And what we want to do is to simulate it. So what we'll do, we will pick some initial state. We'll pick like a funny initial state, which is like, actually I have it here, the project. We'll pick an initial state like this. So we will like stretch the string to begin with. So you can think of it like, take like, how's it called if you have like an instrument like violin, a string, right? And you just pluck it and you just let it go. It will bounce back and forth, right? That's what the solution should be like. And how do we compute the solution? So this is just a second order differential equation. We convert it to a first order system of differential equations. So here this state vector will have dimension, so this y dot and y, so the y dot are the velocities of all the points, and this is a vector from to n. If I have n active particles. So these ones don't count because they don't move, but I'm simulating these ones inside it actually do move. And if I write it in the matrix form, the matrix looks like this. It's really just doing the damped harmonic oscillator, but doing it for every single spring individually. Or basically just putting these equations together. So this ends up being just identity matrix. That's the damping matrix, the damping term, and the T matrix is essentially like a almost Laplacian matrix, and that's the matrix coming from the spring forces. And here the bottom block is just to tie together the velocity with the differential equation. They're really the same idea as in the damped harmonic oscillator. So this will be your project to essentially do this and then simulate it by taking the exponential and plotting it and seeing the spring bonds, which I think is sort of fun. Hope you think so too. Is that sort of clear? Doesn't have to be completely clear at this point. It should be sort of clear. Any questions? Yeah, and then there is extra credit to do this for a 2D membrane, because this is like a 1D case, right? But you can easily think that I have like this, like a piece of paper or something, and I do essentially the same thing. Then you could do it in 3D and so on. All right. Okay, so that is all for today.